Hello and welcome back to the second part of this guided project on credit card approvals, and we'll be using the logistic regression model for this lesson, for this guided project. So we're going to start onto the pre-processing section, and as we saw from our exploratory data analysis up above, we have a lot of outliers, and outliers really negatively affect a model's predictive ability. Doesn't ruin it completely, but you're not going to get the best result from that. So what we want to do is we want to deal with those outliers. So we're going to do handling outliers. The first one, we'll look at the distribution plot of the age column. So we're going to give it the data frame in the first place. In the next position, we'll call x equals age, and then we're going to give it the color hue to approve. So we have a little bit of texture of when they're approved, when they're not. And if we run this, we can see we have a nice long kind of tail right here. It's not too bad, but it is pretty, it's still, there's outliers over to the right hand side. So what we want to do is we're going to do a little bit of engineering and engineer this. So we'll go df, let's give this the age column. So we're going to replace what we have in age with, so we'll go equals to df dot age, closing bracket, dot clip. And in the clip, we'll pass it the upper argument that was already there. And so we're going to go up to the age of 65. So age above 60. 65 really is probably not going to make too much of a difference here. And so we can see here, let's run this. And then let's see what the plot looks like afterwards. And we can see we get much closer to a normal distribution, which is really important. We're going to get, our model is going to find the averaging across the rows to find the best coefficient. These outliers, just like they would pull the mean towards the outlier, they're also going to pull our coefficients for our model that our model learns towards the outliers. And that just might not be true for the whole data set. So something to be conscious of. The next one we're going to do is the outliers for debt. And you can see here a much more pronounced exponential distribution. So let's see if we can deal with that. So we'll do the same thing here. We're going to go df debt, closing bracket, equals to df debt. Make sure we put that in as a string, closing bracket, dot clip. And then inside we'll do upper 15. So let's move everything above 15 down to 15. You can see here where I did it right here. And all these things to the right hand side of 15, we're going to move towards 15. So let's run this and then look at the plot. So you can see we can get a much more, you really wouldn't call this an exponential. It's more of a normal or uniform distribution than there are outliers. This will be much better for our model in making predictions. Okay, the next one we're going to deal with is years employed. So when we look at years employed, we can see a much more pronounced exponential distribution. So we'll deal with this in the same way. So we'll do df square brackets. Let's get rid of this exclamation mark. And so let's go years employed equals to df years employed. And we'll go dot clip, and we're going to give it the upper 10. So we're going to move everything that's above this 10 right here down to the 10. Really just again to make sure that we're managing these outliers, because they really do make our model less predictive than it could be. Okay, and you can see here we're getting a little bit of bias now in that we're getting a little bit of a bump here at 10. But it's still really good. We have a much better distribution than we did. The average, the mean of this is going to be much more representative of our whole data set. So the next one we're going to look at is credit score. And you can see here again, same deal. We have a long kind of right-hand tail. So we'll deal with this in the same way that we've been dealing with our other features. And so we'll go df credit score equals to df credit score dot clip. And so we want to put the upper inside the clip, and we're going to move everything down to 15. So just right down to here, you can see there are some little tails. There's some numbers that go way off to the right, but really we're concerned about, is it 15 or greater? 15 should be good enough. So what we can see here, there we go. We get a much more uniform distribution. This is going to help us find a better coefficient when our model is learning from all of the rows. Okay, so next one we'll deal with is income. We had a lot of outliers in this data. It's a little bit tedious. Sometimes we have to do this over and over again, but this is really important. So it's all about getting to the goodness of a good prediction on our model. So it's good to put this little bit of extra effort in, make sure we deal with all these outliers. So again, we have income, and you can see again a very pronounced outlier over to the right hand side. We're going to move everything down to the inside. So we'll do the same thing, df, and then we'll give it the income, and we'll go equals to df income dot clip, and we'll give it the parentheses, and then inside it we're going to give it the upper argument, like we've been doing in all of the ones above, and we're going to move this down. Everything above 1500 will move down to 1500. You can see here we go out to 100,000. This is a very large deviation in our data set. And so here, if we plot this now, we can see that we get a much nicer looking distribution. Still a little, it's not normal. Normal would be the ideal distribution here, but now the average is going to be much more representative of our actual data set. Okay. So the next thing we'll do is, so that's it for outliers. So now we'll work on dummies. So what I like to do when we start dummies is we do df.columns to get a nice list of our column names. And from this, we can just easily select what we're going to use. So here we're going to use gender. We're going to use married, citizenship, industry, and ethnicity. So we're going to assign those, the features that we want to one-hot encode to a list. So we're going to call them category features, and we'll run that. And then we want to go is df equals to, so we'll go df dot, or sorry, pd dot get underscore dummies. And then in this, we're going to give it our data frame, and then we're going to give it the columns argument, and we're going to assign this to our list of cat features, cat feeds. And so from this, we'll get a list now, a much bigger. And if we were to print out our df columns down below, we can see here, we get a much bigger list, and we want to encode it. So now ethnicity, when it's Asian, it's a 1, and then it's 0 for the other times. Ethnicity, when it's black, it's a 1, and it's 0 for all the other times. All of these ethnicity, the 5 different features that we have now, are all going to be zeros except for 1 that's true, and then all the rest, the other 4 will be 0. And so one-hot encoding allows us to, our model to build coefficients for when the feature or the category is true. Okay, so what we'll do here, so I'll do df.columns, I'll select this, and I just copy and paste here. You'll notice that I'm taking out the zip code feature because really that isn't super valuable. We could do some more engineering to try and group those, but because everyone has a unique zip code, it doesn't help it. We would need to do a lot more engineering to group the zip code by maybe the first 4 digits and see if we can get a good category feature from that. Quite a bit of work, but we could do that if we were not getting good predictions. So either way, what I've done is I made a list of all the features that we want to use, all our new features in terms of the ones that we've engineered, and I've set that to features, and I've set target equal to our approved, our target feature that we want to predict. So I'll run this, and then we're going to go is x equals df, and then in the square brackets features, so all of these columns are coming, and then y is equal to df.target. Okay, so we'll run that. And then just doing a standard train test split. So you go x train, x test, y train, y test. And this is equal to train test split from sklearn. We'll give it our x features that we just created and our y feature or y target that we're going to be predicting. So x, y, and our test size is 0.3. So we're going to hold back 30% of that in reserve. What we'll do is we go into the modeling section. We'll go